there are three major bonding models to consider. A lot of the time at this stage, we primarily consider two of the three, which is what we're going to do here, but we are going to mention all three. Now, when we look at bonding, what is the point of bonding? What are atoms trying to do when they bond? Well, they're trying to attain a full valence shell. All right, and so we're going to gain electrons, we're going to lose electrons, or we're going to share electrons in order to have that full outer shell configuration. So one example to this is when sodium chloride is formed. So sodium chloride is NaCl. So when sodium chloride is formed, sodium wants a full valence shell, chlorine wants a full valence shell. So my sodium ion is going to look like this. We are going to lose the single 3s electron, and we're going to end up with this. Okay, so there is our sodium ion. Chlorine, we want to make that chloride ion. Okay, so we're going to get 1s2, 2s2, 2p6, 3s2, 3p6. Okay, we're going to add in one more p electron. So what elements naturally have a full valence shell? Are noble gases. And so here, my sodium is going to be isoelectronic. To neon, and my chloride is going to be isoelectronic to argon. Right? And so that is the purpose behind our bonding. All right, so I mentioned that there are three major bonding models. Ionic bonding, where we are forming ions. Covalent bonding, where we are sharing electrons, so covalent, co together, valent meaning the valence electrons. And then our metallic bonds, where our valence electrons are donated into the full thing and they all float around and we get this electron C. This is why metals are such good conductors of electricity, is they have permanent mobile charge because of this metallic bonding model that has this electron C and this constantly mobile set of electrons. Okay? So when we look at our ionic and our covalent bonding, which are the two that we're going to focus on here, we need to start understanding what's happening and what sort of properties we get from each of these. So let's look first at our ionic bonds. We have electrostatic attractive forces. I have a cation, I have an anion. Opposite charges, they attract. So there's my attractive forces. Okay, I'm going to make crystalline solids. So instead of having discrete molecules, I have formula units. So again, like my sodium chloride. For a sodium chloride crystal, I don't have a single sodium ion and a single chloride ion. I have this whole lattice network of sodium chloride, sodium chloride, sodium chloride, sodium chloride, so on and so forth in this alternating ion pattern. Okay? So we identify these by empirical formulas. I could have something where I have 100 sodium ions and 100 chloride ions. Well, Na100, Cl100 reduces to NaCl, empirical formula. And typically speaking, these are going to be a metal with a non-metal, okay? Typically speaking. Whereas my covalent bonds, these are shared, covalent, okay? We are sharing. So the electrons are going to exist in between each of the atoms and we are going to share. Sometimes it's an equal sharing, sometimes it's unequal sharing, but they share the electrons. And so whatever's being shared, each atom considers those electrons as theirs, and so they get their full valence shell. We do get discrete molecules. So like if I have a sample of water, I'm going to have a whole network of these discrete little molecules everywhere. Okay, and these can form gases, liquids, or solids. Okay, we use our molecular formulas for these. And typically speaking, it's a non-metal with a non-metal. Now I say typically speaking, because we can get some metal, non-metal covalent characters going on depending on the difference in the electronegativity between the two elements. But most of the time, we're dealing with a non-metal with a non-metal. Okay? When I look at those molecular compounds, what's going on here? Well, they are going to boil at low temperatures and they're going to have weak intermolecular forces that can be disrupted, okay? Now, some intermolecular forces are stronger than others. Do you remember from your prep classes what the major intermolecular forces are? Things like our dispersion forces, our dipole-dipole, hydrogen bonding, okay? And so certain forces are stronger than others, and so certain compounds are going to have, let's say, a higher boiling point than others. Like water has a fairly decently high boiling point for a covalent compound because of the strength of the intermolecular forces, the hydrogen bonds that are there, okay? Whereas our ionic compounds, because they're this full crystal lattice held together, okay, we get high temperatures in order for them to boil, because we're not disrupting intermolecular forces here. We're disrupting intramolecular forces. We're disrupting bonding forces. And so we have strong electrostatic bonding forces that have to be disrupted. Okay. Now, of course, there are exceptions to the rule, like in covalent compounds, something like diamond. We've got this network covalent bond where it's not intermolecular forces that hold bond, diamond together. It's this whole three-dimensional network of that. But for the most part, okay? And so ionic bonds and covalent bonds are going to be the two that we're going to focus on, okay? We'll look some at ionic bonds and our lattice energies that bring these compounds together. And then with our covalent bonds, we will go back to understanding Lewis structures and how we put all of these pieces together.